Saxon Algebra 1, Lesson 74. Greetings, students. Today we're going to be spies, detectives, and we're going to learn to write math in a secret code. This code is called scientific notation. And it's a code that mathematicians can use and understand. It's also a code that works well for scientists. We use it, all of us, when we have very, very large or very, very small numbers. And we need to do calculations with them, but they're kind of a headache because they're so big. And sometimes we take very large and very small numbers and try to mash them together. It can be a bit of a headache unless we use our secret code. So examples are astronomy, chemistry, biology, physics, just as some examples of areas of science where we use our secret code, scientific notation. So the way the code works is there's two ways we have to learn the code. Like any code, you have to learn how to take regular numbers and put them into the code, right? And then the other thing we have to do is we have to put coded numbers, right? We say we put them back into, the word we use is standard form. And all that means is we just make them look regular again, all right? So this is true for using any kind of code, right? You have to take your message, if you will, our message is a number, you have to put it into the code, then you send it to the other person, right? Or whatever you're doing with your secret message. And then that person has to translate it back into regular words, right? So when we're using scientific notation, we have to learn how to do both parts. We have to learn how to take a regular number and write it in the code. And then we have to learn how to take a coded number and put it back into its regular form. All right, so what does this code look like? I'm going to show you right now. In this code, we put the largest digit in the ones place. Now, that may sound simple, and it is, but remember I said we're using very, very large numbers or very, very small numbers. So I take that number and I readjust it so that the largest digit is in the ones place. And the purists among us would say that I should tell you that it's the largest significant or non-zero is another way of saying it, right? And we'll talk about that when we get into this a little bit more, but that's the way I should puff up my definition here to make it more precise, is it's the largest significant digit or the largest non-zero digit. I'll show you what that means later. All right, so we put the first digit here, then we can put in as many decimal places as we need to, right? And we'll talk more about that as we go. But then you multiply this number, that's always just in the ones place, times 10 times the power of 10. All right, let's flip the page and try an example, and you can see what this means. Let me write this out again. It's as many decimal places as we want, times 10 to some power. This is a multiplication sign. This is a mysterious exponent, all right? So let's take the number, example 74.1. There are 4 examples in this lesson. Write this number in scientific notation. All right, we look at that number, we go, okay, that's a pretty small number, right? We said it was for very big numbers or very small numbers. It'll work for anything, but unless your numbers are kind of extreme, you don't necessarily want to go to the trouble to using this code. Okay, so what I said we wanted to do is we wanted to move the first significant or non-zero digit into the ones place. Okay, so that means, and this is where that rule makes sense. We don't want any of these numbers in the ones place. They're just zeros. This is the first significant or non-zero digit. So we want him in the ones place. So we want this decimal, we want it to look like this, right? We want the 3 and then the point and the 1 and the 6. So we want to move this decimal. I'm counting the jumps for every place. I want it here, don't I? I want to move the decimal. So when I do move the decimal, I'll have a number that looks like this, 3.16. Just one digit in the ones place. These guys trail on in the decimals. And then we're going to multiply it by 10. Now, how do we know what number goes up here? The number up here is the number of jumps we need to make to get that decimal from where it is to where we want it. So let's count. 1, 2, 3, 4. We moved it 4 jumps, so we put a 4 up here. But now we need to decide if this should be positive or negative, because that's another part of the code that helps us. If we see a positive exponent, that means, hey, if you want to translate this number back out of the code and into its regular format, you need to make it bigger. A positive exponent means that the real number is bigger or larger or greater or whatever more appropriate mathy word you want to put in there. Okay, so a positive exponent says, hey, when you take this number out of code, make it bigger. If you have a negative exponent, then that means the real number, why am I not writing on the lines? I don't know, is smaller or lesser, whatever you want to say that's mathy, okay? I like to use normal words so that you don't have to decode my writing, right? Okay, so this exponent gives the person who's taking the numbers out of code, do you make it bigger or do you make it smaller? Well, we want to take this 3.16, and if we were taking it out of code, we'd be putting it back into this shape, right? We'd want it to be this number. So we would want to take this 3.16 and make it smaller. So that tells us we should have a minus sign up there. Okay, so this is the number this is the number with the decimal adjusted decimal. Okay, so we didn't change that number other than its decimal place, right? 316, 316. We just brought the decimal over so that the first significant / non-zero digit is in the ones place. And then here, the exponent, the number represents the number of jumps that we had to make to move the decimal, right? 1, 2, 3, 4. And then the sign goes to these rules. A positive exponent means that the real number, the uncoded number, you should make it bigger. And a negative exponent means that the real, the uncoded number is smaller. Okay? So this tells us that the digits are 316, that we need to move the decimal 4 times, and that we should end up making this number smaller. So that would tell us, oh, we need to move the decimal this way, because that makes a number smaller. Okay. Let's try another one. Right here, 74.2. This time, we're getting the number halfway into scientific notation, and we have to clean it up, all right? So this happens quite often in the sciences, where we get a number that's kind of in scientific notation, but not quite. Okay, so we've got this same number. Oh, look, that's the same number we had up here. But this time we're multiplying it by 10 to the minus 7th. That kind of looks like scientific notation, right? That's the times 10 to a power. But this part isn't right, because we should have this set up so the decimal is making this in the ones place. So what we do in this style of problem, which is very common, it's halfway coded and we need to fix it so that it's completely coded. What we do is we ignore that part for now. We just pay attention to this and we fix it. Now we just did that up here, so I'm gonna just quickly remind you. 1, 2, 3, 4 moves. So that will be 3.16 times 10, and then we said 4 jumps, and the uncoded number needs to be smaller, so that tells us we need a minus sign there, okay? That's what we got last time. It's the right answer. I never did this, though. Beautiful. So now we're going to rewrite this part of the number just the way we did. Now we're ready to bring this part in, and look, these two look exactly the same, don't they? They're exponents of 10, right? They're 10 with an exponent. So what we can do is we can use the product rule for exponents to combine those. The product rule for exponents says that if you're multiplying matching bases, you can add them. So this becomes 3.16 times 10. We add minus 4 and minus 7. That becomes the minus 11. Oh. So what we did was we took a number that was partly coded, but not all the way into the proper code, and we adjusted it, so now it's absolutely perfect. All right, let's try another one. $74.3. Right. That's our old friend again. Times 10 to the 7th. Okay, so this problem is a lot like the last one we just did. We have a number that's not in scientific notation, but then it kind of is. So we're going to do it just like we did the last one. First, we're going to adjust this much and make it perfect scientific notation. Then we'll bring him in to the mix. This is the same number we've done several times. We already know it's 3.16, right? Because I moved the decimal to here, times 10. We know it's 4 jumps. Do we want this number to get bigger when we take it out of the code, or do we want it to be smaller when we take it out of the code? We want it to be smaller. So that means we put a minus sign there. Now we're ready to bring this into the mix. And now we pay our attention to putting those two together. It becomes 3.16 times 10 to the minus 4 plus 7. We're adding these. We're using the product rule. So it's 3. Yay. In all of these examples, we are moving our numbers from regular numbers or partially coded numbers all the way into the code, right? That's what we're doing. All right, example 74.4 is John at his cheating best, because what he's basically going to do is make us do 3 problems and pretend it's 1. Okay, here's the way he does it. And this is the way he does it in the practice. No, the practice problems are a little bit different. Okay, he says, write the following numbers in scientific notation. First, he gives us this number, 47,800. Okay, we know that we move the decimal. Now this time we're moving the decimal in the opposite direction because right now the decimal is there. Even though we couldn't see it before, we could draw it in, right? We know it lives right there. Now, we don't want it there. We want it to go 1, 2, 3, 4 places over. We want it right here so that the 4 will be in the ones place. So this will be 4.78. Again, we have 2 decimals. We could have more or we could have less. Don't think that it always has to be 2, just because our problems have been that. Okay, times 10 to the how many jumps? We jumped it 1, 2, 3, 4 times. When we adjust this number out of the code, do we want this number to get bigger or do we want it to get smaller? We want it to get bigger, right? Because we want it to go all the way up to 47,000. So that means this should be a positive 4. So I won't put a minus sign there. We don't usually put the positive sign, but we can. This is the answer to part A. Now, just like we did last time, John is going to take that number, 47,800. We know that's not proper scientific notation because we figured out what it should be. And then he tacks this onto the end of it. So again, we're going to have to follow our 2-part process. First, we're going to fix this part. We know our decimals here. This is the same thing we did last time. I'm just going to do it again to remind you. So we'll have 4.78 times 10 to the how many jumps did we do? 1, 2, 3, 4. And if we want to take this number out of the code and take it back to its actual number, do we want it to get bigger or smaller? Oh, we want 4.78 to turn into 47,000. So we want it to get bigger, so this will be positive. Okay, this looks just like that. Now we're going to bring this part down, 10 to the minus 7, and we'll combine this for our final answer. It'll be 4.78 times 10 to the, we add those together and we get minus 3. Yay. And then the last one is our same original number, but this time it's times 10 to the positive 7. This time it was negative 7, this time it's positive 7. So we do the same thing. First we adjust this number, 1, 2, 3, 4. 4.78 times 10 to the 4 jumps, and we take this number and make it bigger so it stays positive. Now we bring that down and we're going to combine those, and our final answer is 4.78 times 10 to the 4 plus 7. That's the product rule in action for us. Yay! Final answer. Fabulous. We're going to practice using scientific notation for quite a while, and then we're going to start using it to do actual calculations, right? So we won't just be converting the numbers for no reason. We will be using them in bigger problems. If you find yourself in a science class that does math calculations, chemistry is a great example. You may find yourself in a situation where your teacher is teaching how to do these scientific notation calculations. You are going to be way ahead because John does an excellent job of preparing you for these calculations. So be prepared for other students to say, hey, how do you know how to do that? And you'll say, because John's cool, that's why. But no, it should help you a lot when you get into science classes that require these calculations because you will have already had practice. Yay for being prepared. Okay, thank you. Goodbye.